Good morning again. So let's look at the alignment today. So this lesson is about aligning, for example, a new image with an old image. For example, if you take this one, you can see the US flag pole is continuing from the new image to the old image. That means the image has been aligned, as you can see. So this exercise needs for us to compute a transformation called a homography. So we will see how these homographies can be computed using the feature matches across images. And we studied about the SIT features, and these can be matched across images. And also we looked at RANSAC and other ways of fitting some transformation to a given set of points or given set of point matches. So this is the interesting lesson that we have for today in the early part. Okay. So this is what we looked at previously. We had some noisy set of points, which we identified as xi, and then the model that we want to compute. Now for a line, this model can be y equals mx plus b. M and b are the parameters. Or if you use total least squares, ax plus by plus c equals 0. A, b, and c are the model parameters. So what we want to do is to find these model parameters that minimizes the residual between those that are predicted by the model and the actual points. You sum that over all the points. So this you can see a compact way of representing what we have been doing using total least squares or least squares line fitting. Yeah. Okay, so in this lesson, alignment, we looked at how to fit a model to a transformation between pairs of feature matches in two images. You can see now these are not just points, these are point matches. Now you can see given matches. Matches with x1 prime. Xn matches with xn prime. So in this case, as we have drawn in this image, you can think about this xi, for example, as let's say 300, okay, comma 405, let's say. Bad idea. X-axis is, um, I think I will confuse you if I use these kind of numbers. Use some reasonable numbers. So x coordinate can be maybe 50. Okay. Y coordinate maybe let's say 305 or something like that. Now you can see we know this coordinate. In the next image also, we know the coordinate. Now that coordinate, the image has been rotated. So you can see the image will be an array of this sort of size. So you can see the x coordinate and the y coordinate of this xi prime has changed now. So maybe that has turned out to be 152, comma, maybe this one, let's say 400. Oh, these are just random numbers to explain you, okay? They are not correct numbers. Okay. So now you can understand what xi means and what xi prime means. So these coordinates. So we have n of those coordinates. So we want to find this transformation that minimizes the transform version of xi. That means we are trying to match xi to xi prime. And then this is only for I, the second one also, the third one also, and so on to the points in the second image. So these are the points in the second image. These are the points in the first image. So I hope that the problem setup is clear for you. Now the question is, there are two questions. How do we find these matches? Because these matches, if you can mouse click, of course you can find them. Otherwise, how do you automatically find them? That's one question. And the second question is, if you find these point matches, let's say we have 5 of those matches here, as you can see in this image, how do you match them? That means how do you find this? I'm sorry, how do you find the transformation after matching? Transformation T. Those are the two questions. Okay. So why do we do this? For as we saw in to match images, to align images, and for many other things that we are going to learn after this lesson. This technique is very important. So when you fit the T that we are trying to fit, that you saw in the previous slide, can take many forms. That can be a so-called an affine transformation. I will show you what that means. Or it can be a homography. In later lessons, we will understand that they can have other different meanings also. So we want to find this transformation. So we will write down the equations and we understand mathematical ways of finding this transformation in this lesson. Secondly, robust alignment. Now, some matches can be correct, some matches can be wrong. So how do you deal with that? So we saw in the last time lecture, when we looked at outliers in line fitting, to get rid of outliers, an excellent method is RANSAC or MNDSAC. So we will understand how to do this through RANSAC. And then later on, finally, we will briefly look at large scale matching. That means if you have thousands or tens of thousands of images, how do you go about doing this? Because the regular techniques that we use here will not be applicable in that situation. This is what it is. So we will mainly look at the inverted indexing and vocabulary trees. So we will conclude this lesson with that. Okay. So panorama stitching. Now this is a great example that's there in the things like phones also. But the difference between what's there in the phones and what we can do after learning this lesson is in your phone, you have to move the phone in this fashion slowly, right? If you go to the beach or something. But in this lesson, after doing this, you should be able to um, align images, not only like that, but you can see that image can have an arbitrary shape after aligning. It can be moved in different ways, not only horizontally. Yeah. So these algorithms are there, like a auto stitch. Some phones have those, and you take multiple images of a thing like a mountain. It's a large one, and then you can nicely stitch them, things like that. So this is the aligning contemporary and historical images, the look into the past thing. So you can see what the situation would have been in that city in the past, things like that. Here also, right? Okay, and then instance recognition. So, for example, if you ask in this image, can you find the toy truck? You can by doing this feature matching and alignment. In these totem poles, what are these? Where are these icons? And so on, right? Yeah, these are the kinds of applications that you can do. Then instance recognition. So this is Eiffel Tower, recognizing things like that. So by feature matching and geometric alignment, you can do these things. We will look at those things also. And these are large scale recognition tasks. And this is called building a Rome in a day. It's a funny statement, but what that means is you take large number of images, you can reconstruct the scenes in the Rome in a day. That means using a reasonable amount of computational power. Mm, these are actual reconstructions. That means you can rotate them in 3D and V. So this is there if you go to, I think, particular landmark on Google Earth. They have 3D reconstructions. Mm. Let me see if I can access something and show you. I hope it'll load quickly. Okay. Let's search like Statue of Liberty or something. I don't know. I've not done this recently. Okay, yeah, there you go. That's the thing. Yeah, that's the thing. And you can move the man here. You can now you can see that you can rotate, right? I mean, these 3D reconstructed. These are not just images. These are actually 3D reconstructions. I don't know. Some of them are images, I think. Some of them are 3D reconstructions. I think I went too far. Yeah, I went too far. Anyways, you understand what I mean. Put the man. Some books. Okay, you can see it. Are they just images? I hope they are 3D reconstructions. Okay, so you get the point. Mm, 3D is actually a big thing now, based on generative techniques. Also, now people build 3D models and so on. So these ones we will briefly see when we have time. So how do you get about doing this in the conventional pipeline? And in the new pipeline also, you need the initial steps. Find a set of feature matches that agree in terms of the local appearance, geometric configuration. Local appearance means if you think about this little thing, maybe somewhere here, maybe this one, that little thing here, that should look like the thing here in the other image, right? So locally, they must be similar. That's what this means. And what is geometric alignment means? Now think about this, like this point, um, this point, yeah. I'm selecting more than one point, but please understand it's just one point I have to select. This point, and let's say this point. All right. You can see this is some quadrangle thing. In the next image also, that quadrangle nature must be consistent. Some consistency must be there. What is that consistency? That's a transformation that is there across these two images. Estimation of the transformation we are going to discuss in the class today. So that same transformation should have been able to transport the points in one image, image one, to the other. Yeah. Okay. So then you can do this stitching. So I hope you understand the local appearance and the geometric configuration. Local appearance applies to one single point appearing in the two images. Geometric configuration, a set of points it should transport from one image to the other by taking a similar transformation, a similar nature of moving from one image to the other. Yeah. Yes, it's slightly not very easy to visually see that because that the transformation can be slightly complicated. Okay, so we saw that last time. So these are very robust ones. So these images, these points that have been found on the master over image has been able to be located in the other image also. So that really works. So we saw this also due to large photometric changes. Now you can see this is a nighttime image. This is a bright daytime image. Still, the features can be found in both the images. Yeah. Okay. Now we have to see how to actually fit affine transformations. Okay, affine is a simpler transformation. Now let's understand the problem setup and how to solve it mathematically. Yeah. Okay. So we have been given matches x1, x prime are the matches. So example, you can see this is xi, this is xi prime up until xn and xn prime. So don't think that when you write xi, it is just one number. It's two numbers, x and y coordinates are there. Find the transformation T that minimizes the residual, that means the error between the transformed version of xi. Hopefully it will go closer to this. Yeah. when you transform the yellow one, hopefully it will grow very closer to that. Maybe not exactly. Blue one, hopefully it will go very closer, and so on. So now you can see when you transform, there may be some error, right? Some distance between these 2 points, the transformed xi and actual xi prime. This is that error. So there's a distance. This is that error. That's the residual. That's the residual. So we can minimize, if you minimize that residual, you know that this transformation will become more and more correct. That's a problem. Okay, I think it's a very beautiful problem. Let's see how to solve it. Okay, but before doing that, I need to tell you what are these kinds of transformations that can happen in images. Okay, so the first one, I will show examples also that can happen in images is called an isometry. It's very simple. You can see the input points are there x, y, and here we put 1 and extra number. You will see why that 1 is there. Later on, we will understand that slightly deeply. So this one is epsilon cos theta minus sine theta, epsilon sine theta, cos theta, tx dy. Okay. So let me compute what x prime is based on this equation. Okay. X prime is equal to, okay, you know that in matrix multiplication, this term multiplies x epsilon. Epsilon is plus or minus 1. Okay, shall we take epsilon to be plus 1? Then it's easy for us, right? X, because we took that decision, it's easy for us. X cos theta, x cos theta. And here the sine minus sine theta multiplies y minus y sine theta. And then finally, this tx multiplies this 1. So 1 times tx plus tx, right? Okay. So you can write this a similar equation for y prime also. I will not write that. And 1 is 1. There's no change there. So at once you can see the reason for us to have this 1 here. Because otherwise this tx or the translation cannot be captured in this matrix multiplication form or as a linear transformation. So this last one is very important in that case. So you can see new x prime and new y prime can be computed if you know theta, tx and ty, theta, tx and ty. So these kind of things when epsilon is equal to plus 1 is called an Euclidean transformation. Euclidean transformation. The thing about those Euclidean transformations is they do not change the rigidity, geometric structure of the thing. So if you apply a transformation like that to this object, it will rotate and translate. That's all. That it will not shrink. This thing will not shrink. But something that can shrink is, for example, if you try transform this, maybe it will shrink like that. But I cannot show the shrinking in this one. It will maybe turn into a rhombus or something. So these kind of things can happen in slightly more complicated transformations that we have here. Okay, so remember this transformations equation, epsilon cos theta minus sin theta tx, epsilon sin theta cos theta plus ty, 0, 0, 1. So please remember that. So we will code it and see how that transformation happens. Actually, I have them written here, but I will do something right now. Otherwise, because otherwise you will not perhaps See the nice nature of this. Okay, so I imported these. So remember now I have these coordinates A, B, C, D. These are the coordinates 0, 0. Okay, then 0, 1, 1, 1, 1, 0. Remember the last coordinate I just had to put. So here, if I draw this one, if I draw that, we can draw that. So bad idea, right? So this, so we have 0, 0. So take this as x for time being. 0, 1. Oh no. 1, 0. 1, 1. This one is 0, 1. So we can see these are the four coordinates I have drawn there. So after applying the translation, that means tx and ty, and the rotation theta, something will happen to that, right? Maybe it will go like that. But the length will remain because it's a Euclidean transformation. Length will remain. Angles will remain. So you will see that. Angles do not change. But there are other transformations that actually changes the angles and so on. Yeah, we can see that. Okay, so let's go get back to the code. So this is the transformation. You can see 0, 0, 0, 1, 1, 0, 1, 1. So of course, as usual, you are most welcome to ask any question. Either type in the chat or you can turn on the mic and ask. This is very, very important if you have a question for you to ask because then I understand that I'm making a mistake or something. So uh, 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 I need to understand whether you can comprehend what I'm saying. So I'm making mistake in saying that. Okay, now let's construct the transformation. Um, uh, so I have concatenated them to construct this capital X comprising all the points. A, B, C, D, these are all the points are there. So if I print that, if I print capital X, you will see that I have concatenate all the points. See, 0, 0 point, 0, 1 point, 1, 1 point, 1, 0 point. That has been done. Then in the next step, what I'm doing is I'm defining my theta, then defining my translation, epsilon plus 1. Yeah. Okay. So my theta, now I will define that theta. Theta is maybe 30 degrees times, yeah, pi divided by 180 to convert them into radians. And T, the translation, mm, we can write 1 in x direction, 2 in y direction. That's enough. So this is the what I have done. So 2, 1, translation vector, everything transpose also. Transpose. Okay. Now rotation matrix. Okay, now you can see they will directly give me the rotation matrix. This is wrong. Cos theta, sin theta, and we had Tx. Uh, shall I write Tx? It's easier. Yeah, Tx. And in the y direction, Ty. And then that's not all. We had 0, 0, 1. Okay, rotation matrix is there. Okay, actually, this is not the rotation matrix. Only, as we saw in the slide, we had it as HE. So we'll call it HE. HE. Euclidean transformation. Okay. Now to compute, apply the transformation. So to get the transform points, you just have to matrix multiply this. This is matrix multiplication. This is the matrix multiplication. So the plotting code I will copy from my thing. I have the plotting code. Uh, yeah, shall I show you the answer here? So now you can see I have the original rectangle here 0, 0, 0, 1, 1, 1, 1, 0. And Euclidean one, I have done the in the Euclidean one. Okay, let me run that again. For the Euclidean one, also called isometry, uh, I have gotten y1. T is 2 and 1, 2 and 1, T0, T1. So we made a little complication here that I will revert back. This epsilon I want to keep as 1. Otherwise, you will get very confused. Because I wrote the full thing in slides. You can see this point 0, 0 has gone to 2 and 1. 2 and 1 and the orange one is the Euclidean transformation. Now the similarity, second one is called the similarity. So there you have a scaling factor S also here. Scaling factor S. So scaling factor I have put as zero 0.5. So maybe you can put 0.7 or something, it does not matter. And the translation has been kept as the same. So I will change the translation matrix also. T equals maybe not 2, 1, maybe to move it further away, I will put 2 and 1.5 or something. So it will go further away. Okay, similarity. So you can see the similarity. Right? Similarity, you can see it has shrunk the rectangle due to the similarity. It has shrunk the rectangle. Then we have further complicated ones. Euclidean, similarity, affine. So now you can see affine, the rectangle has been transformed into a rhombus. Rhombus. And then homography is very complicated, slightly complicated. So the parallel nature of the lines has disappeared. You can see in all these three, the orange one Euclidean, green one similarity, and red one affine. The parallel lines are still parallel. Now, this line is parallel to this line. So here also this line is parallel to this line, but not here, not in the homography. So this is the action that happens when you change the camera's viewpoint and take two images. It becomes it becomes a homography. Yeah. But right now we are trying to estimate an affine transformation. So all these ones I have I have given today uh, in the slide. So you can see the similarity transformation. And then in the affine one, these are just A11, A12, A21, and A22. There is no relationship like this. So XA, the so-called affine transformation uh, on the input vector X. So this X is a set of points, XY1, A, T, 0 transpose 1. So you can see 0 transpose is these two zeros, right? 0, 0. No big deal there. These two zeros. That's what you identify here as zero transpose. Yeah. The rotation matrix, excuse me, this is that one. Uh, but please disregard these epsilon coordinates. And the translation, you already know, this is the translation vector. And this one is there as it is. The same one. Oh, I'm not changing color. This one is there. So you can see in this case, it's not a sine, it cannot be expressed using sines and cosines and an angle. It is A1, A2, A11, A12, A21, A22. In this case, signified as capital A. So this is what we are going to estimate. Okay, question for you. This transformation, how many parameters does it have? How many unknown parameters? There's a question about the quiz. Yeah, the quiz is for today. So if I have not changed the date, I will change it. It's a mistake. We call it 2D affinity. So can you answer that? 2D affinity, how many? You can just have to count the unknown parameters. Just count the unknown parameters in this. For example, we do not know A11's value, right? Just count them and tell me how many unknown parameters are there. Yes. Some people are giving answers, so those are correct. Who else can try? Please do this. Can others also attempt? Any answers? Only several people have answered. Yeah, can others also try? It's very important to think about this. Give me Sorry about that. A lot of people type 6, which is correct. So you can see. mm, uh, Sorry about that. In this one, there are 6 numbers. Uh, there are 6 numbers: A11, A12, TX, A21, A22, TY. Those are the 6 numbers. And those 6 numbers we have to estimate. How do we estimate? Because we know the point matches. Based on the point matches that we know, we can estimate these 6 numbers. So we will get into that. Mm. Okay, now let's see visually how this looked like. For example, if you take a similarity, that means you have the tiles laid out on the floor. Similarity will just change the size of them, but not the angle. So you can see the 90-degree angles are still there, and the sizes may have changed. But here, the angles are not 90 degrees anymore. Wait, okay, when you look at it, you think they are 90, they are not 90, but the lines are still parallel. Lines are still parallel, you would agree. But if you take so-called homography, projective transformation, the lines are not parallel. You cannot see that they are not parallel. You can see that they are not parallel, right? So these are the kinds of things that happen due to these transformations. Actually, the so-called homographic transformation can be constructed by combining several of them like this. Yeah, you can look at it later in your leisure time. Okay. From the Hartley and Rizerman book, that is a very, very valuable book on multiple geometry, you can see the thing about the Euclidean transformation. So these are the numbers of the rotation matrix. Actually, only one number is there, theta, Tx and Ty. And the similarity, you have theta, and you have this scaling S and Tx and Ty. And then in the affinity, as you counted, there are 6 numbers. Here there are 4 numbers. Here there are only 3 unknowns or 3 numbers. Here there are actually, although there are 9 unknowns, only 8 are meaningful. So we call them 8 degrees of freedom. Yeah. So let's start with this affine transformation. You can see the yellow rectangles, they have changed shape. So they have changed the shape. No, you think that they have not changed the shape because as a human being, you think that they are the same. But you can see, I mean, there's a rotation and then all these things have changed, right? Yeah. A simple fitting procedure, linear least square. So we see how to do that. Approximate viewpoint changes for roughly planar objects. So for the fine transformations to work, these objects must be roughly planar. Yeah, can be used to initialize for more complex transformations. Mhm. Yeah. Okay. Someone is asking a question. Is this last week's recording? Yes, I think. Yes. Uh, yeah, we did 2 parts. Yes, this is the one. Yeah. Okay. So here is the important equation. Assume we know the correspondences. What do you mean by the correspondence? We know that this red point matches with this red point. The yellow point matches with the yellow point and so on. So that means we have 5 point matches. 5 point matches. Yeah. Okay, then we write the equation. So remember the equation had 6 unknown parameters. Those 6 unknown parameters we have written here. But actually, in the previous slides, we wrote x I prime, y I prime, and one is equal to a11, a12. Actually, this is, because I got it from a different book, it is written like that. Tx and Ty, but it's the same thing. Tx. T1, 0, 0, 1, A21, A22, X1, Xi, Yi, and 1. Okay, so this is the same thing that we have written here, with slightly different parameterization. So you can see, as we looked at before, A11 multiplies Xi. So in this case, it is M1 for easiness, M1 multiplies Xi, and then Tx gets added, right? Because of this 1 here. So there you can see this is T1. I'm sorry about the change, the parameterization. Question. So if we have two images to match after detecting key points and correspondences, we can automate with transformations need to be tried or try multiple models. That's a very, very important question. And the question is, now you have the point matches as here and there you have the point matches. Now you want to find a transformation. Is that transformation one single affine transformation, or is that transformation, can that be a different one? Should we select the transformation that you have to put? Now these are slightly uh, questions going beyond this lecture. Here we assume that the transformation is an affine transformation. If we do not know what that transformation is, we have to do estimation of the models. So for that, we have AIK criteria, information criteria like that. There are criteria, different criteria for doing that. But usually that problem does not arise if you know that this is a transformation from one plane of the image to another plane, far away photograph to another far away photograph. Yes, that's an important question though. Okay. Moving on. So you can see we can write this as, if you like, xi prime m xit also we can write like that. So okay. So in this case, the thing that we have to minimize is m times xi. So this is our xi in this case, minus t. Subtract that from the transform version. This one. Any questions about that? Remember this boldface xi prime means xi yi, yeah? Boldfaced xi means xi yi there. Okay, now we know what to minimize. What to minimize is, but we had to write it in a different manner to do that. Okay, so because what we want to find are the values in M, four numbers, M1, M2, M3, M4, and T1, T2, right? Because now, so therefore, we have to write them as here. So now tell me, what is the multiplier of M1? Multiplier of M1 is X1. What is a multiplier of M2? Multiplier of M2 is XY1. What is a multiplier of M3? If you consider the first equation, M3 does not get multiplied, so 0. M4 does not get multiplied, 0. So T1 gets multiplied. T1 is just there, so the multiplier is 1. T2 is not there in the first equation. Because using this, you can write two equations. One equation for xi prime, and the other equation is for yi prime. Yeah, so that's why this set of numbers are there. Okay, then second one is this one. So I hope that this is clear to you how to get these numbers. Very simple. Rearranging the terms in the equation. Okay, so this is only for one point match. Point i's matches. So we have 5 points here. 5 point matches here. For 1 point match, you get two equations. For 5 point matches, how many equations will you get? You will get 10 equations. How many parameters do you not know in this? There are 6 unknown parameters. 6 unknown parameters, right? 6 unknowns. Unknowns. Horrible writing, I'm sorry. But 10 equations. Okay, to find 6 unknowns, how many equations do you need? Independent equations? 6, right? Each point gives 2 equations. So how many point matches do you need? 3 point matches. To estimate an affinity or find transformation, you only need 3 point matches. I mean, this is the thing. Now, it's very simple to think about. Now, assume that you have a rectangle. Okay, this rectangle becomes a rhombus, parallelogram or rhombus or something, right? Uh, what are all the variations that can happen and how many parameters do you need? So when you draw different diagrams like this, you can realize that you only need 3 point matches for that. You only need 3 point matches. With 3 point matches, your transformation is well defined of the parallelogram that you get from the rectangle. Yeah. All right. So how many matches do we need to solve for the transformation parameters? So something like this. So you need 3 point matches. Here's the picture that you want to see. Okay. So this is so solving this we see. Then if you think about a homography, it's not a rhombus anymore. It is just a quadrangle. The result is just a quadrangle here. Uh, So how do homographies arise in real world? So you have a wall like that, and then you can see the 2 viewpoints, right? So here this line is like that, and this line is like that. So you can see that they're not parallel. Maybe in this picture they are sort of parallel, so you can see the different viewpoints of a camera gives rise to homographic relationship between images. The transformation between two views of the planar surface, that is homographic. The transformation between two images, two cameras that share the same center. That means you keep the camera on a tripod and then rotate the camera. That kind of the transformation that exists between images of those rotated points, that's also a homographic. Yeah. So if you want to do panorama stitching, you have two choices. One choice is you get a far away image. That means a mountain or something like that, so that your camera is so far, image is like a plane. Image is like a plane. The scene is like a plane. So you make two of them, you can stitch it. Otherwise, you keep the camera on the ground on a tripod and then rotate the camera and take pictures. Still, they can be stitched in this fashion. Okay, so yeah. All right, so now let's say how to find the homographies. A little thing about converting between so-called homogeneous coordinates and regular Cartesian coordinates. It's this. So you saw that when we wrote those equations, we converted xy to xy and 1, right? We added a 1 at the bottom. But due to some reason, after computation, this 1 is not a 1, but some w. To go back to Cartesian form, you can divide by that number. X divided by w, y divided by w. So this converting from homogeneous to image coordinates, converting to homogeneous form, the image coordinates. So converting from homogeneous image coordinates. Okay. So if you look at the equation for homographic transformation, so even in other ones, so this one is there. When you do this computation, you will get some multiplier. Get some multiplier. So to get rid of that multiplier, you have to divide by the last coordinate of the result. Yeah. So we write this in this fashion. This is the homography. X is this vector of x, y coordinates and 1. And x prime is the resulting point, and lambda is that arbitrary multiplier. Okay. So if you want to fit a homography, the expression is slightly complicated. So we have this equation lambda equals x I prime hx1. How can we get rid of the scalar factor? This is a difficult question. The only way to get to the scalar factor is to do this trick. Yeah, one way. I don't know. It's the only way. I'm sorry. You get the cross product between these two. Cross product. I hope you remember what cross product is. So if two vectors are parallel and if two vectors are perpendicular, what's the situation? So um, uh, let's call this vector A, the same vector. So A cross A, do you remember what this is? If the vectors are parallel, they must result in 0, 0, 0. Zero vector. For perpendicular vectors, dot product is 0. For this one, cross product is 0. This is 0 vector. So that's why they have put the bold face here. It's a 0 vector. Because these are parallel vectors. H, X, I, and uh, they are here they are written as equal, so they are parallel. So we want to get the cross product. So there is a formula for the cross product. You don't have to memorize that. When the objects moving independently, do we have to isolate track those? Some more uniform homography doesn't. Yeah. The question is about a dynamic scene. In a dynamic scene, objects are moving independently. Okay. In these cases, these do not work. These are for static scenes. This is not for tracking. Tracking is some other topic. This is still scenes, and we want to just match them. A good question, please. In this case, you can see we had to do slightly complicated manipulations here. So this H you have to take as for row times xi, second row times xi, third row times xi. So this H, you know that this has three rows, right? This number, this number, this number, this number, this number, this number, and so on. And here you have xi, the xi, yi, and 1. So we are saying that this one we are identifying as H1 transpose. This one we are identifying as H2 transpose. This one we are identifying as H3 transpose. So those you can see now it's okay to write like that. Now because of the cross product, this is what you are going to get after applying the cross product. It's slightly complicated, I agree. So here we have that formula. Then we want to write them, rearrange the terms to get this here, H1, H2, H3. So you can see if you take H1's multiplier in the first equation, H1 does not multiply 0. In the second, yeah, first equation, H1's multiply. Let me think. Yeah, this is 0. So yeah, so this one, okay, anyways, this is equal to 3 zeros, right? If we take the first equation, this equation, H1's multiplier is 0. See, H2's multiplier is minus xi. We have transpose because we have not written transpose here. H3's multiplier is yi prime xi transpose. So these are very easy operations to run in using a language like Python or NumPy. So we have this equation. Okay, something for you to think about now. Okay, think about it. I'll let you think about it. Then I'll adjust the quizzes date. This is nothing other than something like this, right? We have some set of numbers. Actually, if you think about it, there are 9 numbers, okay? Because this 0 has 3 zeros. This x1 has 3 numbers. This y1 prime is a constant, xi prime has 3 numbers. So there are 9 numbers here. So h1 has 3 numbers. h11, h12, h13, and so on. Finally, it's up to h33. There are 3 numbers there. 9 numbers there. So this is a 9 by 1 matrix. This is a 3 by 9 matrix. So in reality, what you have is forget about all these things, some matrix multiplying some another vector. And it turns out to be zeros, a set of zeros. A set of zeros. My question is, what is a very simple solution for this one? If you substitute what, will you get 0? If you substitute what, will you get 0? Okay, I change the quizzes deadline. Okay. Can someone think about it? What can be a solution for this one? If you put what numbers here, will you get all zeros? You must if you substitute zeros, you will get all zeros. Because like something times 0 is 0, right? So this is a simple thing. Like if you have something like some number like 5 times a, you're saying it's 0. What is the possible value of a? Of course, 0. Okay. But that solution is not helpful for us, but it's a zero homography, not correct. What we want is non-zero solution for H1 to H9. So to establish the non-zeroness, we have to apply a constraint for that to solve this. These equations say, yeah, the thing is something is. So for that, we have to use the so-called homogeneous least squares to find H, minimizing H squared. Find H, minimizing H squared. This is what we need to do. Otherwise, the trivial solution is the solution. Solution is given by A transpose A, eigenvector of A transpose A corresponding to the smallest eigenvalue. So this, if you don't understand this, memorize this. The solution is given by A transpose A corresponding to the smallest eigenvalue. So this smallest eigenvalue can be calculated. This eigenvector can be obtained using single value decomposition in MATLAB or in NumPy or something. So if you are given a system of equations like this is not computer vision. No? This is solving a homogeneous system of equations. Homogeneous means the right hand side is zero. If the right hand side is zero, you have to go for the least squares, homogeneous least squares. In homogeneous least squares, uh, the solution is obtained by you get the matrix. This is the capital matrix, A matrix, uh, A transpose A. Uh, 0, the solution is, sorry, A trans AH is equal to 0. The solution H is found by uh, eigenvector corresponding to the smallest eigenvalue. What is the minimum number of matches needed for a solution? A has 8 degrees of freedom, 9 parameters, but scale is arbitrary. One match gives us two linear independent equations, so you need 4-point matches. Yeah. Okay, we are understood how to do that. Now, should I show code or do I have code? Let me see that for that. Homographic transformations are there. Have I computed the defined matrix somewhere? No, I have not done that. But maybe if you want, I can give an example. This is transforming an image using given homography. Let me see the trans. So here is that one of the graphite images. If you apply a homography image 2, you can see it's transformed, right? It's rotated in this fashion. And other transformations are applying. So uh, this is transforming the first image back onto the frame of this image. So now they look the same. They look similar. I hope you can see that. So this homography is given with the images. So I am reading that homography H into this file. So if I know that homography, I can transform image 1 using that H called warp perspective. In this case, you can see we are not finding the homography. We are given the homography in this graphite image sequence. So I'm reading, you can see I'm reading that file called H1 to 2P, that file. In the next example, transforming the second image onto the first. So this is the first image. This is the second image. Now second image I'm transforming into the first. So you can see the rotation has to be like that, right? So you can see it as I made a mistake somewhere. That's why this is happening. So you can see it has happened. I don't know what that mistake is. Computer the homography is a mouse click point. So I have this code also. You can click using mouse and then you can do the transformation. So I have given the code which I have uploaded or I will upload so that you can try it out in your own. So you had to, I usually click 5 points. So I had to remember what you're clicking. I click this point, this point, this point, this point, this point. In this one, I had to click the same point in the same order. This point, this point, this point, this point, this point. So you can see it has sort of stitched, right? The two images. There is some problem here because if we properly stitch, this line should continue, right? These lines should continue. They are not continuing. See, there is some break here. The reason for that is our mouse clicking is not very accurate. These points must be sub-pixel accurate. So if you use a um, software for that, we can get sub-pixel accuracy for computing the key points. That is SIFT, if you use SIFT. So let's see robust alignment, how that is done. Robust feature-based alignment means we have assumed that we are given a set of correspondence between two images and we want to align. If you do not know the correspondences, what's the situation? So we have to do robust feature-based alignment. So extract features in both the images and then we match. So you can see obviously there are incorrect matches. There are incorrect matches. But by looking at it, you know, you can see from the geometry, you know that some matches are incorrect. For example, this match, you know that it's incorrect. This match is incorrect, right? You can see that for sure. And there are the incorrect matches also. So what I said was this point matches should follow some pattern. Okay? They must sort of rotate as a bundle, right? Yeah. So that's the property we are using to good filter bad points. So extract features, compute putative matches. So we compute some matches, maybe correct, maybe not correct. Then using these three matches, we hypothesize a transformation. Okay, this can be the we compute using the previous algorithm, transformation T, and verify uh, transformation search for other matches consistent with T. So you can see this is a random sample and we find the consensus. And then, yeah, can do that. So generating putative correspondences. Need to compare features and descriptors for local need to compare feature descriptors for local patches surrounding each interest point. So to generate patches, you take you run a shift and then for each of these points, it will give a feature descriptor. Last time we looked at them. So the other points also have feature descriptor. So you try to find the best match using those descriptors. Question. So to apply transformation in this case too, we need to make sure it is static in this case. How can we make sure that like rolling ball match which has unique pattern? So if we calculate the error, it may give high value but hard to detect. Is there such a scenario to where we have to very intuitive about even static images? I don't fully understand the question. I think the question is about if the object is dynamic, what is the reason? If the object is dynamic, this does not work. There are solutions though. If the object is slowly moving, you know, the objects do not move very fast. We can do feature tracking on that. Feature tracking, that means find features that are moving with the object. So this is another field called feature tracking. If the object is dynamic, the matches will not be very correct. Uh, if the motion is very small, we can use a thing called optic flows. Optic flows can handle small motion. If the motion is large, then we have to use feature matching. And then the feature matching has to happen different motion parameters will have to be computed. One for the background, one for the object. Yes, it is possible. Okay. So feature descriptors. So we recall features versus feature detection versus feature description. Detection means we find scale space extrema points, if you remember. those points that can have a x, y scale and so on. So those points we call these features, and at each of those features, we have to have a descriptor. So one descriptor can be the image patch itself, but the problem is when the image patch is there, so in another image it will appear very distorted. Simple descriptor vector of raw intensity values. So when you have raw intensity values, it is possible to compare, but it's very bad because of the changes in viewpoint and illumination, there will be a big change. So we can use the sum of square differences. It's very easy. So here is patch number one in the image one. Here is patch number two in image two. So uh, maybe you have these are 21 by 21 patches or something. So these are equal size patches. You subtract each element and square it. If there are 21 patches, 21 is the dimension, then 21 times 21. Let's take an easy one, 7 by 7. So 49 numbers. In the other image also 49 numbers, other patch also 49 numbers. Subtract each of those 49 numbers, square and something. This is called sum of square difference. It is okay, but the problem with this is when patches are bright, it will get higher value. Or differences and so on, it will be a problematic. Then this depends on the number of elements in the patch also. So that's why we need to assign a descriptor rather than using direct patches. Then if you are just concentrating on the intensity, what we can do is we can subtract the mean before doing this, subtract the mean and subtract the mean, and we can divide by the standard deviation. Mean center and divide by the standard. That is called normalization, right? Like z-score computation. Why would you prefer normalized correlation over SSD? SSD is sensitive to the illumination changes. SSD is dependent on the value of those and the number of elements in the patch. That's a problem. So disadvantages of those, if you use patches, as you can see, small deformations can affect the matching score a lot. So this one is slightly deformed, you can see. So value here and the value there because of the deformation are entirely different. That's a problem. That's why we talked about the SIFT features. SIFT features are very robust to those things. So divide the patch into 4 by 4 sub patches. Compute the histogram of gradient orientation 8 reference angles. So for each of these patches, for example, this one, we compute all the gradients in vertical direction. What is the amount of gradient? In horizontal, what is it? So for 8 of those. So resulting descriptor is 4 by 4 times 8, 128 dimensional descriptor. It's like a signature. So this signature, as you saw in the master over image, can be matched across large variation of intensities and viewpoints. What are the advantages of descriptor or raw pixels? Gradients are less sensitive to illumination changes because if it is dependent on the gradient, if you remember, Laplacian of Gaussian is what we use. So it is a gradient based operator. So not sensitive to illumination changes that much. Pooling of gradients over a sub area. So you can see here, we have sort of done some pooling, right? So take this patch, whatever the gradient in that patch amounts to this one. So slight location changes are okay. So pooling gradients over sub patches achieve robustness to small shifts, but this preserves some spatial information, some spatial. Okay, so in this case, we can generate the so-called putative correspondence, that means matches that we think are correct. For each patch in one image, find the short list of patches in the other image that could match it based solely on the appearance. So if it go for slowly on the appearance, rejecting ambiguities will be problem, right? So now think about this example. Here you can see this F1 is we want to match with one of these. F2 prime and F2, they are the same, right? They look the same in that window. So therefore, the feature matcher can make mistakes. Heuristic compare distance of nearest neighbor to that of second nearest neighbor. So this is a measure that David Lowe used. So Yeah, if two patches are the same in both the images, their distance will be very low. And the distance to the second nearest neighbor will be large. So this is a technique that David Love used. If you need more information about it, I can talk about it. So rejection or ambiguous matches, how can we tell which putative matches are more reliable? Uh, it's very hard. Heuristic. Compare the distance of the nearest neighbor to the second nearest neighbor. This is what David Love did, as I said. So ratio of closest distance to the second closest distance will be high for features that are not distinctive. So this graph is from David Lowe's paper. PDF for the correct matches. These are the correct matches. These are incorrect matches. For correct matches, closest to the next closest ratio will be small, like zero point 0.4. But here, closest to the next closest will be very large, quite large. Yeah, so please think about this a little bit. Okay, so even after aligning in this fashion, there are outliers. To get rid of outliers, we have to do ransack. Solution is ransack. So what is the ransack loop? Randomly select the seed group. So seed group means to do a fine transformation, we need 3-point matches. To do a homographic transformation, we need 4-point matches. So randomly pick 4-point matches. Compute the transformation from this seed group. Compute the transformation from this seed group. Find inliers in this transformation. So after computing the transformation, we do a matching and find the inliers. That means that agree with this. So remember last time the exercise that we did, I asked what is your age? Someone say a number, and I asked who agree with that. That means who are the people who are of the same age. So therefore, I can get an estimate of the age of this class, right? If I do that questioning. So this is random sampler. I get a random sample, very less expensive, and consensus. And I ask who agrees with that. Then when people agree with that, I select the people who agree and average their age. So find the inliers. Those people who agree are called inliers. If the number of inliers is sufficiently large, recompute the least squares estimate of the transformation of all inliers. At the end, keep the transformation the largest number of inliers. This is the ransack loop. So here is a pictorial review of the ransack loop. Okay, you can see the putative matches here. Two matches are incorrect. The red ones are incorrect, as you can see. Green ones are correct. Okay, so you uh, select one match, count the outliers. So because this is a translation example, we only need one match to do that. So let's pick this match and see how many inliers are there. All these are inliers. So that must be a good match. These are outliers. So again, pick this one, find the consensus. There's only one consensus, and all these red ones are outliers. So that's an incorrect sampling. So the correct one is this one. So you take all of them and average. I hope that is okay. I'll run the animation again. Okay, so you can see in this image there are 1, 2, 3, 4, 5 correct matches and 2 incorrect matches. Then, okay, we don't know about this now. So what we do is we pick one match and then see those that agree with that. Oh, all these 4 agree with that. And then this disagree. Okay, the consensus is 4. And take another one. Only one agree with that. Consensus is 1. So that is has low consensus. So all these things disagree. So that's not bad. That's not good. And the good one, good batch, correspond to this green one. So take all the green ones, average and find the translation. So why do we need only 1 point match for this? Because translation, you need to estimate only X translation and Y translation, right? So 1 point match can give that. But if you want to compute the affine transformation, you need 3 point matches, 3 arrows. If you need to compute the homography, you need 4 arrows. Yeah. So you can see the average has been computed. Image has been translated like that. Okay. Uh, then there's a thing called half voting. If you like, you can have a look at it, but we will not go through that. Uh, Half voting. Okay. Then we have this large scale alignment part. I will go through that very quickly. Um, Now, please give me a few minutes for that, but I will not talk about it too much. The case that we are considering is if we need to align test images with thousands and millions of images in a model database. How do we do that? Then you can see computing, okay, set feature computing and matching with each image is not an easy thing to do, right? I hope you understand the computational complexity of that. This is the computational complexity of that. Now you assume that you have one image, another image. Let's say you have 1,000 points here, 1,000 point, okay, and here you have, let's say, 2,100 points. Okay, assume, okay, let's say this is 1,500 points in these 1,000 to 1,000 points, and if we match them, let's say we matched 1,000 points. So to do that 1,000 point matching, you have to compare all the points at all the points. So that itself is expensive. Then question like real-time face matching is something like that. So now, if you have 10,000 images like that, you can see the computational cost, right? You have to take each of the images and match with all the 9,999 with this kind of a computational complexity. This is the hard thing. Yeah. That's why you have to have proper algorithm for that. Efficient P2 match generation, approximate descriptor similarity search with inverted indices. Okay, we'll see what that is. So this is the scenario. We have large number of images. In all these images, image 1, image 2, image 3, image n, you can see the shift features have been found. That's why they are drawing little rectangles to show those shift features. So here, input feature in the new image. So think about this, there's a new image and it has these shift features computed. And now all these images, shift features are in a database. But that database is like a dictionary. Now think about a dictionary. Dictionary is very different from a book. Okay, if you take a book that will have words, we take a book that will have words. But a dictionary, if you give a word, it will tell you, okay, book one has this word, book two has this word, book three has this word. Right? It's an inverted index. So here in this one, we have the inverted index. What that means is if you are given a shift feature, it will tell you, okay, these images, image 23, image 21, and so on, have that image. So image 23, image 7, and image 97 has that feature. And if you take the purple feature, it will tell you, okay, these images have that feature. If you take the maroon feature, it will tell you, okay, these images have that feature. So based on that, you can see, you can pick the candidate images that match the original image, right? Because you have the inverted index. So I hope you can see the value of that inverted index. So, but the thing is now when you have millions of images, your servers will have to spend time in computing features and storing them and computing the inverted index. And the features also will have to be quantized. That means it must be a vector database. Yeah, these are the things I think Google did in their initial image search. Now I don't know how they do that. So this is the inverted indexing. Then ranking and geometric verification. Then you need the geometric verification. That means features will have to move together, right? move together. So that means one homography should sort of handle all the features. So this is the geometric thing. So to do the indexing, we find visual code words, which descriptors are quantized, because we cannot, a feature is a 120 dimensional one. You cannot have all possible features in the world. It's infinite. So you have to quantize them. So these kind of things are done. So for example, you can see a code book here. What that means is, you take all these patches. Here it's a patch based one, not the feature based one, and say, okay, this one represents that. You take all these and say, this one represents that, and so on, right? Like a monitor representing a class or something. Yeah, of course, these are based on similarity measures. So you can see all these wheels are represented by this wheel, and so on, right? So this is the so-called code book. So every feature that you compute is quantized into the code book. Then you can do clustering. We want to find k cluster centers and assignment of points to cluster centers to maximize the sum of squared Euclidean distance between each point and its assigned cluster center. So these cluster centers are those code books that we have. Yeah. So that's the thing. So algorithm. So randomly initialize k cluster centers. Iterate until convergence. Assign each data point to its nearest center. We compute each center as a mean of all points. So here's an animation. Now you can see the cluster centers have been identified, and you find the distance. This k means clustering. So some clusters get a lot of points assigned. Now, once you find the ones that are, now you find the mean again, average of those points. Then you again find the distance. Then you find the mean again. So you can see the k-means clustering happening. Now it's nicely clustered. So these cluster centers are the C ones, they are the code books. So whenever you get a new one also, you put them into, if they are close to this cluster center, you take cluster center as the representative feature for those. I hope you understand this. If you don't, so please spend some time through the slides. So how do we do the indexing? Cluster descriptors in the database into the codebook. At query time, quantize descriptor into the query image to the nearest code vector. So those code vectors are the ones we showed as the centers. So now you can see it's quite fast. Problem is solved? Not really. There are other things. So you have to use the hierarchical, all kinds of things are there, because it's still clustering is problematic and so on. Uh, Please see these slides, and if you like, you can see the tutorials and the information to learn more about these things. Yes. So when a test image is given, what happens is also there. Okay. Yeah, now I think we can take a break. We can take a break. I'm sorry for taking a little more time. We can meet at 12:30. Yeah, I'll pause the recording. Okay, so we start the cameras as a part. Mm. So we'll briefly study cameras, and then in the next lesson, we will study how to obtain the internal parameters of the cameras, so-called camera calibration. Then after that, we'll be ready to understand how two cameras work, and then how to make a 3D reconstruction. So that's a line of lessons that we start from now. Okay. First, we look at cameras with lenses, and then we look at the concept of depth of field, field of view, lens aberration, and some digital sensors. So you can see some old cameras. So in these cameras, I don't know whether you have seen this. The cameraman comes with a black cloth covering him, uh, and then he puts his hand and opens the shutter, and then closes it manually. This is how cameras were a long time ago. Now, of course, you know that these digital cameras do everything. Okay, so this was an experiment done by a famous person called Paul Debevec. What he did was he took a camera and he removed the lens from here and he put a cardboard here with a small hole. And then he obtained an image. When you obtain an image, okay, there was a little bit of blur. I think this is Paul Debevec. And at the corners, there was darkness. And this is called vignetting. Um, we will see why this happens. This is the pinhole model, famous pinhole model. We have used this when we were small, when we had toothpaste tubes or something. And I hope you remember this kind of thing where we had some toothpaste, not toothpaste tube, toothpaste box or something like so. And there was a small hole made here. And we put another toothpaste box inside this. And then this is a this is a little tissue that we paste onto that. Some tissue thing you paste onto that. This is inside, of course. And you were able to sort of slide it also inside that if you wished. Slide it. So if you had something like a scene or something here, something like a tree or something here, and you get a upside down image on that, right? When you look from this side. So this is called the pinhole camera. So why is the image upside down? The reason is the light starts traveling like that and reaches there, and light starts traveling through the hole and reaches there, and it's upside down because of that reason. So this is the experiment that Paul Debug has done here, but with using an actual camera so that he can record what he gets on the CCD. Yeah. So here is the picture of actual picture of this, the cartoon picture of that. It's quite nice, right? So I hope it is clear to you why that happens. Okay, now one problem that you observe here is the image is blurred. What is the reason? How can you make it sharper? The reason for the blur is obviously this, right? Now there is a finite length to the hole that we make, right? Assume that this is the hole. Yes. So if you take the tree like that, and this is the film, tissue paper or something. This is the tissue paper. If you take one point on this tissue paper, yeah, the light from this point can come to that point. I think you will agree. Not only that, light from this point can come to that point. And the very extreme is light from this point also can come to that point. Can you see that? From here, from there, and from there, and from all in between points, light can come. As a result, this point will get light from different parts. And due to this, there is blur. I hope that is very clear to you. So there is no one-to-one matching between the scene and the image on the film. So now you can see why when the hole or the pinhole is large, then there is blur. Then we make it small. Make the pinhole small, then sharp. Very small, sharper, very, very small, very sharp. Then to make the image extremely sharp, can you make the hole as small as possible? Infinitesimally small? Can you answer that question? To make image extremely sharp. I don't know what that means. Extremely sharp. Can you, is it okay to make the pinhole as small as possible? Can you answer this question? Where are the answers? No. That's, yeah. Can we get some more answers? One person is saying no. Some more answers. His answers are correct. Thank you very much. So I don't know whether everyone is paying attention. Uh, the reason is low light. If you make it small and small, light becomes low and lower. So therefore, your imaging device will not be able to make an image. Not enough. But that's not the only problem. One more problem will occur: diffraction. So diffraction is what? Diffraction means light bending at an edge. You know, the light bends at an edge. So you can see, so when you make it very small, light bends at an edge and diffraction happens. Because of these two reasons, low light and diffraction, you cannot make the pinhole as small as possible. Because our sensors, the CMOS sensor or the CC sensor needs sufficient amount of light to come and strike it, sufficient amount of photons to come and strike it for those elements to collect sufficient electrons to send out so that it can be sensed. Yeah, so that's the reason. So therefore, what people do is people add a lens. So what is the thing about the lens? Now you can see when you add the lens, the one-to-one correspondence is achieved. That is, one point in the image now corresponds to one point in the sensor. You can see why. Because of the lens. Because lens focuses light. Okay, this also. There's a thin lens model. Rays passing through the center are not deviated. The projection model still holds. All parallel rays converge to one point on the plane located at F. So those are two rules that we learned in O levels and A levels, right? Yeah. Okay. Uh, so there's a specific distance at which the object is in focus. Other points projects to a circle of confusion in the image. So for example, if you now the focusing happens for this plane, the focusing happens. If you take this plane in that, the focusing will happen somewhere here. So on the film, there is blur. So you can see the distance between the film and the lens is very important. So this is called the circle of confusion. So okay, we'll briefly look at the thin lens formula, which we have done. What is the relation between the focal length, the distance between the object from the optical center, uh, the distance object from the optical center, and the distance at which the object will be in focus, d prime. So this is the image plane, this is the lens, this is the object. So from this object, there will be light coming, and this light um, has to get focused. Uh, this is the image plane. So similar triangles are there everywhere. So you can see the similar triangles, right? This triangle and this triangle are similar. This triangle and this triangle are similar. So you can see this distance is d, this distance is y, this distance is d prime, and this distance is y prime. So because of that, y prime divided by y must be equal to d prime divided by d. Also, there's a similar triangle again here. So you can see y prime divided by y is equal to d prime minus f, that is this distance, this distance, this distance divided by f, this distance. You can see that this is the same height as y. So using these two formulas, you can obtain this famous thin lens equation: 1 over d prime is equal to 1 over d is equal to 1 over df. Yeah. The focal length concept is very important, and there's a thing called depth of field. This is very important. What that means is at a certain range of depths, we think that exactly at a certain depth, right? Exactly at a certain depth, the image is in focus. But in reality, it's a small range, right? The image is at focus at a certain range. So here you can see, here this is the depth of field. These are not focused. These are not focused. These are in focus, depending on the distance from the lens to the scene. So in a camera, you can control the depth of field by controlling the aperture size. So let's see, aperture means the opening in the camera. You can see a picture of that. Mm. Here you can see the aperture is large. When the aperture is large, let's see now the light can pass through from places like this, from places like this to places like this. Now consider point 1. Point 1 light goes like that, and strikes this place. This ray goes like this, and strikes this place. This ray goes like that, goes like this, and strikes this place. So you can see one point in the scene corresponds to a range of points, a blob in the scene. So there is blur. Plane of the first point, this point, is not in focus. Think about plane number 3, green, focusing somewhere here, right? Somewhere here. So not in focus. So there's a circle there. So there's blur. But if you take plane 2, this plane, you can see exactly the rays that go through the lens meet here. So therefore, there it is focused. So we can see when the aperture is large, some planes are in focus, some planes are not in focus. But if you make the aperture small, light can go through only a small opening near the lens. So therefore, every single plane, this one, and this one, are sort of in focus. Because slight differences are there, are sort of in focus. Okay, so this is the aperture. So a question for you. If you are making a photograph of, a landscape, for example, mountain region, should the aperture be small or large? So can we try this question? So please try this. I have typed a question in the chat. No one is answering. Landscape. Should the aperture be small or large? Some answers are coming. It's correct. A lot of people answering. Yes. Yes. Thank you for these answers. The answers are correct. The aperture should be small. Why? Because we want to focus the close by mountains and far away mountains. Everything you want to focus. So the aperture should be small. If you're making a portrait picture, that means a picture of a person, should the aperture be large or small? Aperture must be large because you only focus the facial area and you want to blur the background. If you see if you just search on Google for images of this nature, you'll see that this is how the cameramen do that. Let's say type portrait images and just check some portrait images. I didn't even properly type it. So you can see, yeah, you can see, where is it? Yeah, so the girl is there. So you can see the background is blurred. The face area is in focus, right? So you can see this is how portrait pictures are made. You you let the background be blurred. Background is blurred out. Only the person is in focus. In all of them, it's like that. That's the right way to make a portrait picture. You can see. Good example, right? Background is blurred. Yeah. But in landscape images, let's take a landscape images. So some Yosemite or something like that. I'm beautiful. Yes, everything is in focus. Everything is focus. So you can see the close by areas as well as far away areas are in focus. You do that by keeping the aperture small. But what is the problem of keeping the aperture small? The amount of light coming in is small. When the amount of light coming in is small, then you have to do other things to the camera. You have two choices. One choice is to keep the shutter open for a long time. You keep the shutter open, a lot of light comes in and strikes so that there's enough photons striking the CCD or CMOS to produce uh, electrons to be sensed. Um, Keeping the shutter open for a long time for a landscape scene is okay because nothing changes in that. But if you do that when something is moving, then there will be motion blur. And the other problem that can happen when you have the uh, okay, the other thing that you can do when if you want to have the shutter aperture small is to increase the ISO value. ISO means the sensitivity of the CCD sensor. If your ISO value is large, your sensor is so sensitive, then you can have enough sensation. But the problem is then the noisiness will be there because it is electronic amplification. Yeah. So these are things. All small aperture increases the range in which the object is approximately in focus, but small aperture reduces the amount of light needs to increase the exposure. This is called exposure, ISO value. So here you can see large aperture, small depth of field. This is a large aperture, we call it small depth of field. So you can see not focus, not focus, focus. Here everything is in focus, small aperture, everything is in focus. Okay, then there's a thing called field of view, how much area the camera sees. Field of view is the angular extent of the world observed by the camera. What determines the field of view? Actually, it is the tan inverse. You can see this angle is what we need to measure. This angle, that's tan inverse d by 2 divided by f, right? So this angle, d. So large focal length, small field of view. Yeah, small focal length, large field of view. So which is what you see here. So if you have large focal length, we call it 17 millimeter, you can see everything. Yeah. But if you increase the focal length, and now here it is 85, you sort of see a small portion. If you increase so much, you only see the things on the ship. Okay. And then changing the field, so people can do different things. For example, if you are far away and you use a zoom lens, 135 millimeter zoom lens, then you can have a small focal length, shorter focal length, but you can move close to the object. Both these things can keep the object at the almost the same size, sort of the same size. But here there is 3D nature. You can see that some 3Dness is there, right? Here the 3D nature is gone. So especially large FOV, small f, camera is close to the car. Small FOV, large f, camera is far from the car. So if you're making a picture of a girl or someone, if you keep the f very small, then you have too much 3D nature in the face. She will not like it. She will hate you for making that picture. And if you're very far from the person, focal length is very large, then their face will become too flat and she will not like you. But if you pick the appropriate focal length and be not too far, not too close to her, then face will appear nicely and she will be happy about it. Okay. So then there is this thing called, you can see now, if you use a short focal length, then your 3D nature will be there. You can see the line, that those are the lines that are actually parallel will not appear to be parallel, right? They are not, in the image, they are not parallel. But here, the lines that are parallel in reality are sort of parallel in the image. We call it weak perspective. So these kind of things are there. Sometimes in movie industry, people make these images. They have the track dolly, right? So they can move the camera back while increasing the focal length. So nice effects can be made with those. So you can see these movie clips if you like. Okay, so we'll study the depth of field and the field of view. Now we'll study the problems that happen during due to lenses. So if you are doing a computer vision work and your camera is not an expensive one, and then sometimes you have to correct for these things. So real lenses, they are made of a large number of glasses. So I have heard that these glasses are cooled over time. So they are made from molten silica, right? So cooled over time so that the homogeneity is kept. This homogeneous nature is very important. So one flow is called vignetting. Vignetting, that happens at the edge of the lens. You can see the light that escapes, right? So light escapes. So therefore, at the corners, you will see darkness. That's called vignetting. Then this is called radial distortion. So if you take a picture of a grid like this, if you don't see distortions, then you will see straight lines. But pincushion distortion, it's like a pincushion, right? You have 4 pins here, like a pincushion. And this one is barrel distortion. This one is barrel distortion, pincushion distortion, this image. This is barrel distortion, right? So then there's a thing called spherical aberration. Spherical lenses do not focus light perfectly. Rays further from the optical axis focus closer. That means these rays, they focus closer. Rays somewhere here, they focus somewhere here. So this problem is there. Then chromatic aberration is lenses have the different refractive indices of different wavelengths. That means you have the blue light, the green light, and the red light. They will bend at different angles. So near the center, there is no problem. But at the edge of the lens, you can see colors because of that reason. So that's why good lenses are very expensive. They compensate for those. Then we look at briefly digital sensors. So people have CCD sensors and CMOS sensors, but usually now the sensors are CMOS sensors. A digital camera replaces the film with sensory array. Each cell in the array is a light-sensitive diode that converts photons to electrons. Two common types, charge-coupled devices, CCD, old, and complementary metal oxide semiconductor, CMOS. So this is how it works. So then there's a thing called Bayer grid. I think we briefly looked at it also. Now, there's only one array of sensors, okay? So you don't have three of them for three different colors. Usually one array, but there can be very expensive cameras that may have two, three sensors. So how do you get the color sensation? You have filters on these pixels, green, red, and blue. So when you have the blue filter, only blue light comes in, like so. When you have the green filter, only green light comes in. When you have red filter, only red light comes in. So I explained this, I think, question for you again. Uh, yeah, someone answered barrel distortion. Thank you. One more question. ISO value feature in the lens or other electronic measures? Yeah, good question. ISO value is a part of the camera body, not the lens. Yes, ISO. Yes. Actually, it's a property of the CCD. Question for you. Why twice as many green pixels as red or blue? I hope my English is correct. Why twice as many green pixels as red or blue? Can you try to answer that question? Okay, no one is answering. That is because of the sensitivity of the human eye. Human eyes, yeah, excellent, thank you. Yes, human eyes are more sensitive to green color, so they use green. They use twice as many green pixels. I mean, there is no one color has to be twice as many. This is how you can cover a 4 by 4 with 3, right? 2 by 2 area with 3 pixels. So because of this reason, some pixels have red, some pixels have blue, some pixels have green. So those pixels that do not have red have to be interpolated and found. What is the red value here? So this is what is shown here. You have to interpolate and find the other value. So this is called demosaicing. Every camera sensor has to do that inside the camera. They have to run this demosaicing operation. So they have complicated algorithms. Why more green? Because of this problem. Luminous sensitivity of the human eye. Okay, so you can see problems with demosaicing also. So when you demosaic these striped patterns, you can get artifacts. So this is color more. Find black and white details in images misinterpreted as color information. Sometimes because of the detector's nature. Okay, so miscellaneous artifacts, noise, low light is where you most notice noise. Light sensitivity, ISO, is a noise trade-off. So then sometimes there are stuck pixels also. So if we make all colors equal, we just don't see much beauty in the image. The question, if we make all colors equal, we don't see much beauty in the image. No, you cannot make all colors equal because you are dividing a 4 by 4 region, right? Sorry, a 2 by 2 region, right? This is how we divide, no? 2 by 2 region. So we have the three colors R, G, and B. So how do you put them? There's no choice. If you put R here, you put green, you put green, you put blue. One of these have to be put twice as many. That's the reason. So we have to make a choice. Choice is you are more sensitive to green, so pick that. In camera processing, over sharpening can produce a halo, something like that. Compression, so in compression also artifacts can come. You know that inside the camera they compress the images to JPGs. Blue means CCD charge overflowing into neighboring pixels can happen. I think this is, I'm not sure what this artifact is. Then color artifacts. Then color more purple fringing, motionless, uh, micro from micro lenses and so on. Those can happen. So you can read about this a little bit more. My knowledge is very limited. I do not know about cameras too much. Yes. So a little bit of history about cameras. So people have known about the pinhole camera a long time ago, BC, uh, 390 BC, and Aristotle must have known about the camera. And then principles of optics, including the lenses, have been known to these people. Camera obscura, Leonardo da Vinci, this year. First photograph, 1822, and these things. Photography film, 1889. Cinema, 1895. Color photography, 1908. Television, 1920s. First consumer camera with CCD, Sony. First digital camera, Kodak. Yeah, these are some histories. This is the first scan photograph or something. So cameras are skyrocketing, as you know, because of the because of the large number of phones that are there. Yeah, that's about the cameras. So those are the things that we wanted to discuss today. Um, if you have any questions, I can answer. Okay, then I will, because we have few minutes, I will briefly show you what will happen next in the class. Then we will look at, from next time, we will not look at it today. We will look at camera calibration. What that means is we are going to understand the cameras mathematically. We will see how images are made. And then we will come up with the matrix called the camera matrix. It's a 3 by 4 matrix. And that 3 by 4 matrix, up to a very good extent, characterizes the camera. Then, so this is that 3 by 4 matrix. 3 by 4 matrix. So this matrix includes the parameters of the CCD sensor also. Sensor is there inside. So we will understand how to relate between the parameters of the sensor to the millimeters in the image. That means if you know the actual distance to the camera, actual distance to the camera from the imaging plane, so assume that my object is on my table and we know the distance, and we know the camera parameters, we can make some measurements. So we will understand how to make measurements. Those are important if you are doing industry automation or something to measure things. So this is the importance of the camera calibration part. And then there are ways of obtaining those camera numbers. So we print a pattern and then try to make that many photographs and obtain that. And then for that, there are mm, ways of solving those equations. So I will talk about them. Then we will slowly start looking at multiple view geometry. What happens when there are several views of the image? You can see this statues has several views, and you can match the features using the SIFT features that we have done. I will show an example also. And then you can make the 3D estimation of that point, 3D reconstruction. So we will see theoretically how that is done, but getting this theoretical the pipeline to work in reality is a little bit hard. So there are three problems called triangulation, motion estimation, and structure from motion. We will look at those things in the next week. So all these things are based on this multiple view geometry book. I have a copy also with me. It's a very, very, very important book by Richard Hartley and Andrew Sisserman. I'm happy to say that some my students have worked for Professor Richard Hartley in Australian National University. I have not seen him myself, a very reputed person in computer vision. So his students have done extremely well. Uh, I will turn off the camera and maybe talk about some of those students later on. Yeah. Yes, that's something that we have to do next week. Then after that, we will have to look at single view geometry. So mainly we will look at what happens when you take an image to the 3 points in the scene, 3D points, X, Y, Z, 2 points on the image. So it's a 3D to 2D transformation or something. So we will look at that, how that happens, and so-called how lines seem to meet, what is horizon, all these things we will understand, the action of a camera, and how to sort of obtain a camera calibration using images itself, we'll understand in that lesson, and making some measurements using cameras. Then finally, in that area of study, we will understand the so-called epipolar geometry, where we understand when two cameras are looking at one point, how do you uh, relate the two cameras to that place. So those are the things that we will study in that. And then the last lesson in this section is the structure from motion, where we study when you have multiple cameras looking at the same picture, maybe not two, more than that. How do you make a 3D reconstruction theoretically? Yeah. These things are very important. So these have advanced a lot now. If you there are topics called 3D Gaussian splatting. These start from points that this so-called structure from motion generate. Uh, and you can see they have 3D reconstructions. You can see now that that's a 3D reconstruction, so you can move the camera around. So, for example, this one, see, 3D reconstructed. So they are showing how that was obtained in this one. So this is Gaussian splatting is a newer technique. Then there's called Mipner-Fossum. So this is a slightly older technique, but that's also still good. I think it's nerve synthesis. So you can see the 3D reconstruction. You can so fly arounds are possible. These are done with images. Mm. You can see the depth also. Depth. Like closer ones are blue, further away ones are red. Beautiful, right? This is what people have been able to do after following techniques like that. So the theoretical understanding that we get is very important for those things.
Hi, I'm John Barron from Google Research.
Yeah. So that's we will not study about 3D Gaussian splatting on Earth, but if anyone needs to understand, of course, I'll be very happy to explain. Mm. Okay, so that's all we want to cover. So if you have any questions, you can answer. Otherwise, we are done. You can log off. So thank you very much for participating in the class on a Saturday, which is not easy for you, I know. Now, by the way, if you wish to come here and do some practical classes with me, I'll be more than happy to come on a Saturday uh, after the classes or whatever. Or if you can come on weekdays, okay, that's easier for me. And we can do some practical classes, do some coding. So remote classes are not the thing that makes me happy, but this is the mode of this degree program, right? Yeah. So if you're willing to come, I'll be more than happy. Okay. Then we'll conclude like this. So thank you so very much. You can log on.
Thank you, sir.
Thank you.